today, so 4:45. Okay, so just to let you know. My lecture is gonna, well, so as Neil said when he started his lecture, that he has a point of view of how he wants to do things and how he wants to do the dimensionality reduction. I also have some kind of a message that I want to convey in the talks that I want to do. So initially I thought of just giving a pure information theory course, and then I thought for the type of people that we have, maybe it's better to give an overview of why I think machine learning might be good for information theory. Okay, what kind of problems they are solving nowadays in information theory, in which machine learning can bring a fresh look into those problems, and also what kind of difficulties we can find on the way in order to solve those problems. So I think I'm going to be talking mainly about a simple example, which is channel coding. But there are two things in information theory that are relevant nowadays, which is network information theory and non-asymptotic information theory. And in both of those problems, I think machine learning solutions can really bring benefit to the type of problems that they are looking into. And I'll try to explain as I go along. I'll do a summary at the end to see if I can explain that better. So my idea here is just to show how to solve the channel problem with LDPC codes, which is roughly using belief propagation, which is we could say it's a machine learning algorithm, although it has many phases, and you can see it also in communications, you can see it in transportation. There are many other ways that you can derive belief propagation. But the way it was used to solve the channel coding problem, it came from a machine learning point of view. And I think that's important to talk about. So I'm going to start showing a few things in information theory and which type of problem I'm going to be working on. And I'm not going to give a lot of information about communications or information theory, but just enough for you to know exactly what we want to do. So the main problem that we have is we have a source of information that we want to transmit to another end through a channel. That's the whole point. Okay? So we have a source that gives us symbols that can be text, can be voice, can be video, can be anything that you want. Okay? And it has a certain probability measure. Okay? And we want to convey that information to another end. Okay? And we want to do, before we do that, we want to do two things. The first thing is we want to compress the source. Okay? We want to take out all the redundancy that there is in the source. So if we have less to transmit, it will cost us less. Okay? So you can know an image, a video, voice, music. It is very redundant sources. So we want to compress it as much as we can. Okay? But then we're going to transmit that through a faulty channel that is going to introduce errors into it. So once we've taken out all the redundancy there is in the source, we're going to add control redundancy. And we're going to add control redundancy to get rid of those errors that we're going to get into it. So those are the two main points that we want to do. First, remove redundancy so we transmit less information, less bits. And then add redundancy in order to control the errors that we have into the channel. Okay? And the thing that we have and the results that we get is that the source encoder has to compress the source to some rate above the entropy of the source. Okay? So if the entropy of the source is 5 bits per second, you have to use at least 5 bits per second. If you use less, the source is not going to be recovered. Okay? And actually, the minimum, the equality sign is what we call the minimum rate that we can submit. And then the channel encoder has the opposite thing. Is you have to transmit information at less rate that the channel can take. Okay? So if the channel is introducing error at a certain rate, you have to transmit less information at that rate in order to be able to recover the information. Okay? So roughly it's telling you, okay, if you have 1 bit per second that you want to transmit, but the mutual information between the input and the output is 0.5, it means that for each information bit that you're putting in, at least you have to put 1 redundancy bit. So your total rate is only 1 bit of information every 2 seconds. Okay? That is what is telling you that lower bound. Of course, these two rates, they have to be equal. So if the rate that you're encoding, the source encoding is higher than the other one, there is nothing you can do. Okay? When we do R equal to the mutual information between X and Y, is what we call channel capacity. Okay? And actually, we have to maximize with respect to your input distribution. Okay? But the thing that we are thinking in here is that we cannot optimize over the input distribution, the X, because that's going to be given up by our source. Okay? So what actually it happens in most cases is if the source encoder works correctly, it will give you an IID source of equiprobable signals. That's the best thing that you can do. And then most of the channels, that will be the optimal distribution for most channels. And then we can achieve the channel capacity. Okay? So now I'm only going to focus on this problem. And then there is one thing that is called the separation principle, that it tells you that you can do both things separately. Okay? That is, it doesn't hold always. Okay? For example, for network information doesn't hold. But when you do point-to-point communication, it holds. And roughly that is the way we've been designing things. So you can see source encoder, you can think of many different things. So you have JPEG, you have MPEG, you have MP3s. All these standards are roughly doing source encoding, trying to reduce the redundancy of the source to independent and equally probable bits. Okay? Lempel-Sill algorithm is the same thing. And then in the transmission rate, we have also a set of algorithms trying to get R as close to the mutual information and reduce the probability. Okay? I'm going to talk about those in a little bit. But we have always designed them separate. So we're going to have the source encoder, you're going to have somebody that is an expert in the source, trying to compress the source as much as it can. And then you're going to have a channel encoder expert that is going to try to put the redundancy in the smartest possible way, okay, in order to get to the capacity. So that you have to put in the least amount of redundancy into the bits that you want to transmit. Okay? I'm not going to get into the proof of any of these things, but I'm sure you remember the example that Niels put the first day about the white and the yellow, and that when you tend to infinity, the green part, the one that is in the middle, took all the probability risk. That's roughly the proof to get those values. Okay? The thing that I didn't say is that in order to get to those values, you are going to get zero. You are going to have a probability of error, of making a mistake on the other end, as small as you want. Okay? If you transmit below that rate, or if you compress above it. Okay? And those are the main results that I'm going to be talking about. So right now, what I'm going to be concentrating on is in this part. How can we introduce redundancy in order to protect the information that we want to transmit? Okay? So we're going to assume that the source or the source encoder give us a set of symbols, okay, all the way 1 to the m, and the channel encoder is going to give each one of these symbols a string of bits, up to n bits. Okay? Typically, we will use C for those, but in order to make sense of all the machine learning that we were doing, I'm going to be using X during that. And if the message that comes from the source encoder is also binary, we're going to assume that we have K bits. And all over the talk, K is going to be less than N. Okay? So we're going to use K information bits, and we're going to add N minus K redundancy bits. Okay? That additional redundancy bits should allow us to find errors and correct the errors. Okay? And if this R is less than the mutual information, as we make N and K tend to infinity, we should be able to correct every error that appears in the code. So we can get an errorless communication if we make N and K large. Okay? Those are the results of channel coding. That if you make the rate low enough, you can get an errorless communication through any communication channel. Okay? Those results are due to Shannon in the 40s, and they were remarkable because in the 40s they thought that the only way to get errorless communication was to get error zero rate. So you have to put more and more redundancy in order not to get any errors. And what he proved was basically that you can get errorless communication at a finite rate. Okay? And since we knew that this limit exists, we've been trying to design encoders and decoders to get to that. Okay? And that's roughly what LDPC codes achieve. We're going to be talking about during the lecture. Okay? So the first thing that we're going to do is talk about linear encoding. And the thing about talking about linear encoding is, if you think about the problem in encoding in general, if you're going from K bits to N bits, that's an exponential problem, either for the encoder. Okay? Because we have to have a table that says each of the inputs, how did they go to each one of the outputs. So we'll have to have a 2 to the K table saying what is the mapping from one to the other. If we use a linear encoding, that's only quadratic in the number of bits that we want to transmit. So we're going to use, and this is something, it's weird, but I'm going to be using row vectors. When we did these type of things in channel encoding, everything is row vectors. So it's completely the opposite than everything else, but it's a standard way of doing it. And I don't want to change it in case you look at everything. So M is a row vector of K components, and G is a K by N matrix that converts the K initial bits into N bits. Okay? And all the additions and multiplication and modulus too. Okay? So we're only going to be working over bits. Okay, I'm not going to put it not to cloud the information. And there are several results, I'm not going to talk about them, but linear channel encoding is good enough to get to capacity. So we are not losing anything for not using linear and non-linear mapping. And the other thing is, you can always prepare the G matrix to have an identity matrix and a P matrix. So the first N bits is going to be a copy of your message. The last N minus K bits is going to be the redundancy that you add to the information. Okay, so X in that, if we use G in that sense, is going to be M and some redundancy bits. Okay, yep.
Is there any darker bits? Do you have any?
Yeah. Better? Okay. And the other thing that we typically assume is that the channel working in independent realizations. So we expect that every time that we transmit a symbol, a noise is added to that bit, independent from any other of the noise to the other bits. If that doesn't happen, well, we'll be talking about a completely different problem, and we don't want to get into that. But this is a good assumption in most communications system of interest. Okay? And when I say it's IID noise, so depending on if P of y given x is a Gaussian channel, CI is going to be Gaussian. If it's a binary symmetric channel, CI is going to be a Bernoulli random variable. Depending on which type of channels do we think, CI is going to be one distribution. Okay? But it's typically known when you design the system. Okay? And the maximum in the channel decoder, the objective is to find the maximum likelihood solution. So if you look from the point of view of the maximum likelihood, the function is pretty simple because it is a product of the marginals and it should be easy to optimize. The problem comes from the restriction, because we need x to be a code. Okay? That's the main issue, and that is what in general makes the problem exponential. So we need to try every possible solution in order to get to that. Okay? So I didn't tell you about this, but the full objective of solving this problem is that we want at least linear complexity in the encoder, and we want at least linear complexity in the decoder. Okay? If we have the possibility of exponential complexity, the problem is very simple. Just choose the word at random and it works. Okay? That's what Shannon proof does. Okay? But that will give you exponential complexity. And I'm sure you all remember Robert's slides with the exponential complexity, that it really blows in your face very, very soon. Okay? So what we want to do is we want everything to be linear complexity, or as close to linear as we can. And that's the thing I want. Okay? So the next thing that we need in order to get to what we want is what we call the dual space of G. Okay? And the dual space is an orthogonal, so G defines a linear subspace of dimension k. So H is a linear subspace of dimension n minus k that is orthogonal to G. Okay? And H is used to compute the syndrome. Okay? So when we transmit the word x and we get the word y, in the decoder the first thing that we can do is multiply that by the matrix H transpose. Okay? And the matrix H transpose and the syndrome, it only depends on the noise. Doesn't tell you anything about x. Okay? And that is pretty easy to see, which is x times H transpose is n times G and that's equal to 0. Okay? You're going to see that in all the examples that I'm going to use, minus P is going to become P. Or minus P transpose is going to become P transpose. And this is only because I'm working with binary symbols. Okay, so minus 1 is 1. Right. But if we were working with other type of symbols, you need the minus on top. Okay. Again, the syndrome uniquely identifies the error pattern that we're looking for. But again, it's an exponential table. Okay. It's going to be, we'll have 2 to the k entries, and as k and n grows with a fixed rate, it becomes exponential. So it's not really going to give us a solution. Okay. Okay. So which type of solutions have been given to these problems? Okay. So this is a very short summary of what we have, and then we have the first thing that we came up with algebraic codes. So I'm sure most of you have heard of Hamming codes. And who has heard about Hamming codes? Most of you. Golai codes? Okay, very few. Red Muller codes? Red Solomon codes? Okay. So those are the type of codes that were designed from the 40s until the 70s. And the objective there was always to use something that is called a cyclic code, which instead of using this matrix, it could be encoded with a linear time machine, with a linear complexity, and they were designed in order to maximize the distance between the words. Okay? The idea was to put all the words as far as possible from each other. Okay? And then the decoders, they only corrected up to the half of that distance, so the number of errors that they have. And that seems to work fine, but as you get to high dimension, there are many areas of the space that you don't explore. So you cannot get to capacity with them. Okay. So they are very nice algebraic constructions, but they are unable to get to capacity. The good thing of all these codes is that the encoding is linear, you can do it in linear time, and the decoding, you can do it in linear time. And for example, the Red Solomon codes, you can find them in your CDs and DVDs. That's the algorithm of choice in order to decode those standards. Okay? In the 60s, we came, I think it was 59 actually, we came up with what we call the convolutional codes. And then they also have a linear encoding and linear decoding, but in order to, for a fixed memory. But in order to get to capacity, you have to make the memory go to infinity, and the decoding is exponential in the memory. So you also couldn't get to capacity. And then in the 90s, from the 90s, we have turbo codes and LDPC codes. And the idea there is going back to what Shannon told us, which is try to use random codes. Okay? And try to get always the best answer that we can. Okay? So algebraic code and convolutional codes are very good if you're only thinking about a few bits, 50, 100 bits. But if you get above that, the ideas that we have in low dimension that work well don't carry over to high dimensions. That's the main limitation of algebraic coding and convolutional codes. Okay. When you go to LDPC codes and turbo codes, they work well when you go to very high dimensions, 10,000, 100 dimensions, 100,000 dimensions. That's when they start working properly. Because random code, do you want? That's when they start working properly. Okay? And when I say the coding and decoding is almost linear, and we'll see that, the encoding, you have to use the G matrix, which will be quadratic, but there are algorithms that you can simplify to make it almost linear. And the decoding, we'll see an algorithm that is linear, but as we get to capacity, we need more and more iterations. So it's not going to be exactly linear. It's going to be a little bit. But for a fixed rate, it's going to be linear. Okay? And they are almost achieve capacity. For example, for the Gaussian channel, I think they are 4.5 to 10 to the minus 3 dB decibels to the capacity. So they are as good as they get. Okay. Why did I put 63 over there? So actually, in 1963, Rob Gallagher proposed these LDPC codes in his PhD thesis. Okay. He proposed the codes. He proposed some algorithms to decode them, but he wasn't able to prove that they were good enough, and they were completely forgotten afterwards. Okay. It took until 1995 that David Mackay recovered the idea of LDPC codes and was able to prove that they were very good and very close to capacity. So we lost 30 years. We lost 30 years now. Okay. So now I want to get to the how LDPC codes work, and there is a tool that has been used for a long time in information theory, which is a Tanner graph, which is trying to represent the variables and the G matrix and the H matrix into a graph. Okay? It is just a factor graph. Okay? I don't want to tell a lot about graphical models because you will have Subin telling you about them next week, and I'm sure he's going to do a much better work than I do. The only thing that I want to do is just give you enough information to follow what we want. Okay? And I'm sure the way he's going to tell them is probably much different than what I'm going to be doing, so I guess it's going to be complementary anyway. Okay, so let's say that we have a parity check matrix, that H over there. Okay, you can see the I and the P structure that we talk about. I interchange them because I usually do it that way, but you don't care because you can flip the columns around. So you have an identity matrix and a P transpose matrix on the other side. Okay, so what do we know? What is the restriction that we have over x1, x5, x6, and x7? Anyone? And over x2, x4, x6, and x7? Or the other 4? So just remember that x for H transpose has to be 0. Okay? So it means that if you look, x1, x5, x6, and x7 are the 4 ones that I have in the first row of H. So I have a 1 in position 1, 5, 6, and 7. Okay? So when I multiply x by the first row of H, I should get a 0. Okay? So that's a parity constraint. Those 4 bits, they add up to 0. Okay? So we can either have 4 zeros, 4 ones, or 2 ones and 2 zeros. Any other possibility is not allowed. Okay? So we're going to represent that in a graph the following way. Okay? So these circles over here represent the variables that we are transmitting. The x1 all the way to x7. Okay? And the lines connect to what we call a factor, which is the row of the matrix. Okay? So the first row is connected to variable 1, 5, 6, and 7. And we call this is a check node because you have to check that the 4 variables add up to 0. Okay? The next one is connected to 2, 4, 6, and 7. Okay? And the last one is connected to 3, 4, 5, and 7. Okay? And that's what we call a tunnel graph. It's also called a factor graph. It's also called a bipartite graph. The bipartite comes from the thing that we have variables on one side, factors on the others, and the variable can only connect to the factors, and the factor can only connect to the variables. Okay? And for this one, there is a nice rearrangement, which is the following. Okay? It's the same graph. I just put it in a way so the lines don't cross, and it's easier to see. Okay? I laid out, so we have the 4 bits that I have over here will be the 4 information bits, M1, M2, M3, and M4. And the X's that I left out are the ones that are the redundancy bits. So then it's very easy to use this graph in order to do the encoding. Okay? So for example, if I put a 1, a 0, a 0, and a 0 here, then we know that this has to be a parity constraint. If I have a 1, a 0, and a 0, that guy has to be a 1. This guy has to be a 1 as well. And this guy has to be a 0. Okay? So we can also use the graph for encoding purposes. Okay? That will be x1, x2, and x3. This is one. Right. Actually, we don't care because we don't put it any order that way. Okay? It's clear how I constructed the graph from the H matrix? Yes. Okay? So now we're going to try to use this graph, okay, in order to get the maximum likelihood outcome. Okay? So or actually we're going to do something different. Okay, so the maximum likelihood decoder, as we said before, it was the argument of the maximum of the probability of y given x. Okay, and instead of putting x to be a code word, we can do this with a different operation. So we can say that we're looking for the maximum of all possible x's, in which we have to maximize the likelihood and make sure that all the parity constraints are fulfilled. Okay, so that will be a delta function. So if x h transpose is equal to 0, we get a 1, otherwise we get a 0. Okay, so we need to fulfill all those constraints and then maximize the likelihood. Okay, again, the solution in this case is exponential in L in the general case. Okay, and then there is also a different problem that we sometimes want to solve, which is what we call the bitwise map. Okay, so the bitwise map solution, what it does is it uses base equation to flip the solution, and then we use for the maximum for each one of the bits individually. Okay, so the map solution is identical to the ML solution in this case. Okay, because all the words are equally likely. Okay, but the bitwise map solution is not identical to the ML solution. Okay, and the way to see it is in the ML solution we enforce that the word that we get is a code word. Okay, in the bitwise map solution we try to get the best solution for every bit. We don't care about anything else. So given all the information, all the y's that I got, for the first bit, what is the best value? For the second bit, what is the best value? And so on and so forth. And that doesn't have to give you the optimal. And a real code can give you something that is different from a real code. Okay? Of course, both solutions are pretty close. And in most cases, they coincide. But there are cases that they don't. Okay? Yep? Can you speak up?
Is there any specific reason you do bitwise?
Yeah, we will go into that in a minute. So there are two arguments to those. So if we do the ML solution, what you make sure is that you get the minimum probability of getting a word incorrectly. Okay? So you will get the least error rate in words, in the number of total words that you're translating. If you do the bitwise map solution, you get the minimum probability of error in the bits that you are receiving. Okay, so those are the two arguments for the two of them. Okay, so the second one is optimal at bit level. The first one is optimal at word level. But the thing that we're going to use the bitwise map solution is still exponential. The complexity for getting the optimal solution is the same one. The only thing that we've got is that there are tricks in order to try to get the solution in a linear term. Okay? And that's what we're going to go and use the graph. Okay? So the idea is, let's try to use the graph in order to get a linear solution, an approximate linear solution to the bitwise map solution in linear terms. Okay? And that's something that we cannot do for the ML solution. So the idea is, even if we wanted to get the ML solution, we're going to use as proxy the bitwise map solution, because we can compute it in nearly linear time. Okay. This is just coming again to the same thing. So we first compute the maximum a posteriori solution for P of x. Okay, and again, P of x given y. If P of x is uniform, the maximum of this will be the same as the maximum of that. But we want to get the bitwise map solution, so we're going to add all the bits and set xi equal to vi, and then once we get this thing, we have to decide which one of these is larger, if v equal to 0 or v equal to 1. Okay. The thing is, this sum is in general an exponential complexity, because we have to compute 2 to the power of n elements, and we have to do 2 to the power of n minus 1. It's actually minus 2 sums. but that is if we ignore the graphic structure. Okay, let's try to use the graphic structure in our favor, and if we do, we can really simplify the solution. Okay, that thing is something that I prepared in 2009, where the joke was kind of fun. Not okay, so I draw a graph. Okay, I draw a graph where we have 7 variables and 4 factors. And if we want to compute the solution, we will have to do the sum for x2 all the way to x3. I'm going to compute p of x1 for all those factors. Okay? And to simplify things, because I don't want to be carrying all the y's over here, I'm assuming that I incorporated the information from the likelihoods in each one of the factors. Okay? Like this is a function of x1, x2, and x3. The probability of y1 given x1, I can put it in there. Okay? The same with 2 and 3. The 4, I can put it in D. The 5 and the 6, I can put it in B. And the 7, I can put it in C. Okay? As y is something that we observe, that we know, it's something that is fixed. So we are not going to care about it. So I don't want to carry a lot of variables that we cloud everything that we do. Okay? So we just have the 4 factors. And if we do this sum, we have to compute 128 elements. We have to add up 64 of them for x1 equal to 0, 64 of them for x1 equal to 1, and then compare them in order to make a decision. Okay? What I just did in here is I rearranged the sums. Okay? I rearranged the sums in a way that is going to be convenient for me. That is going to make all these, doing these sums, pretty easy. And I'm going to start from the end, from the right-hand side, and I'm going to be computing the sums one by one. Okay? So the first sum that I'm going to do is x7, and I'm going to assume that x5 is fixed. Okay? So if I do that, I only have to compute 4 terms. FC for x5 equal to 0, 7 equal 0, and 0, 1. And for that, I get a function that is only a function of x5. Okay? If I'm adding x7, I only get a function that depends on x5. Everybody sees that? Okay? If I put this in a general way, so factors could be anything. If our factors are parity check factors, actually the one on this one and this one will have to be 0. Okay? But you can do this for any factor. They don't have to be parity checks. So this is when I put the whole thing. For computing this sum, I need to compute 4 components and perform 2 sums. Okay. And now I'm going to do 2 sums at the same time. So I'm going to do this one of x4, that if you look is the same one that we did for x7 before. And I'm going to do this one, which is x5 and x6, and I'm going to get a function of x2. Okay? Forget about this b going to x2, they will mean something afterwards. Okay? The important thing here is that I get a function of x2 when I sum x5 and x6, and I get a function of x3 when I sum x4. For this one, I need to compute 8 components and perform 6 sums. For this one, it's again the same thing for each. And for the last one, I'm going to add x2 and x3. And the thing that I'm going to do is, again, I have to compute 8 components and perform 6 sums. Okay? And now we know that p of x1 is proportional to this RA of x1, this function of x1, and we just normalize. And when we normalize, we get the, if the probability of x1 is greater than 0.5, then we'll say that the map solution is x1 equal to 1. If it's less than 0.5, we'll say that the map solution is x1 equal to 0. Okay? I'm sure all of you have been counting, but you can see that we only do 26 computations and 17 sums. So it's an order of magnitude less than if we have done everything else. Okay? That's the beauty of rearranging the sums. That once we do it that way, we can do everything in a much fewer computation. And we've been using the graph structure in order to do that. Okay? The good thing is, as we've been doing this thing, we also recover the partition function. The C value, which is going to be the same one for all of them, we can get it from the sum of these two values. Okay? And for the other marginals, we have to do a little bit more of work. Actually, if we wanted to get x2, we have to rearrange the sums in a different way. If we wanted to get x7, we have to rearrange the sums in a different way. Okay? So that seems like a little, I mean, even if I did this very fast, now you tell me, okay, if I have to repeat these things for each one of the variables, at the end I'm going to get the same complexity. Okay, so I'm not making anything. The good thing is we don't need to sort the variables. We can do it without sorting the variables. Okay? And this is what the message passing algorithm, and what the notation that I was using before is helpful. So if you remember, the R's of the name of the factor to a variable, what it was telling is the information that each one of the factors knows about that variable. Okay? And that's a local computation. So in this case, each one of the factors is going to send a message to each one of the bits about the information that they know about the bits. Okay? And then the variables is going to send to the factors the information about what they know about themselves. And you're going to iterate until that algorithm converges. Okay? And when it does, you get the bitwise max solution for each one of the bits. Okay? So the idea is very simple. I'm a variable x1 and I want to know what my value is. Okay? So I expect all the factors that are connected to me to send information that they know about me that I didn't tell them before. And I'm going to tell each one of the factors the information that I know about myself that they didn't know about me. Okay? This algorithm works, and it works in a finite number of iterations if, and this is a big if, the algorithm has no loops. Okay? I plot the graph in a way that you don't know if it had loops or not. But it's easy to see that this is the graph that I was using. There are no loops. Okay? When there are loops, there are two things that you can do. Okay? There is something called the junction tree algorithms that it tries to collapse variables together until you get a loopless graph. And then you can apply this algorithm. And then you can do the engineering solution, which is all the messages that I'm using are local. So from a local perspective, I don't know if there are loops. So I still use it. Let's see what happens. Okay? And if it's worked, why should I worry? Okay? And that's actually what we do. Then we worry when it's not working. But initially, we don't worry about it. Okay, so let me remind you about the message so we can see it. Okay, and what I'm going to do is I'm going to add a factor now for each one of them, incorporating the information about y. Okay. Okay, because this is the best way that we can incorporate the information about y in each one of them. So just assume that I have and assume there is a y at the end of each one. Okay? So the factor, the variable is going to send to each factor the information it knows about itself that the factor ignores. Okay? So x2 is connected to A, B, and E2. Okay? So it has to send information about to x2, to A, to E2, and to B. And it has to send all the information that it knows about itself. And then the factor has to send information to all the bits or all the variables that is close by. So A has to send information to x1, x3, and x2. And the important thing here is that you don't need to replicate information. Okay? So we call the message from the variables to the factors is all the information that x2 knows about itself that doesn't know the factor already. Okay? So x2 sends the information that it got from B to A, and it sends the information that it got from E2 to A. But we don't multiply by the information that A already has about us. So we don't multiply by R of A to x2. Okay? And the factors do the same thing. They get the information from the different variables. So they get the information from x2, from x1, and x3. And they also have the factor function. They have to add for everything that you have in the factor. Okay? And then they send that information back to the node. So in a way, is what I just said is x2 tells the factor everything that it knows about itself that the factor doesn't know already. And the factor says you have to fulfill several conditions. That's the factor. And I have this information from these other variables that you don't know, so I'm going to send it to you. Okay? And here is what you can see the problem when you have loops. When you don't have loops, the factor knows is sending always new information that the variable doesn't know. But when you have loops, all this information propagates through the loops, and you can get a feedback of the same information that you already saw through the loop. Okay? What we always hope is that that information is distorted, so when it gets to you, it's not really going to change what you know about yourself. Okay? Again, sometimes those things don't happen. Okay? But we will worry that in a second. Okay. So this is the algorithm, and then it's easy to prove that the complexity of algorithm is linear, because if you don't have the number of iterations that you need to converge is the maximum path in your graph, and each one of the operations you expect that in each one of the factors you have a finite number, a very low number of variables. Okay. So it will be exponential in those variables, but if those variables remain fixed, it's not exponential as you increase the graph. And I think this is what I want to break. Okay, no, this is the next one. And this is just, I didn't want to put this equation initially because every time people see the general equation, they just say, hey, this doesn't make any sense. Okay? So the only thing that I'm saying in the first equation is you have to multiply all the information that you get from the other factors, except the ones that you know about yourself. So xn sends information to j of all the other factors, except what it knows from j. And m, the cardinalities, the set m has all the factors that are connected to xn. Okay? And the variable to factor is the same thing. You have to add for all the variables except the one you are transmitting on, and you have to multiply by all the messages that you got except the one that you got from that one. Okay? Those are what these two equations say. Okay? And this is the algorithm that we're gonna try to analyze. Okay? So the important thing about the message passing is, first thing is we don't need to sort the sums. Okay? The sums are already, we can do this message passing without sorting the sums. Okay? And we don't need to know the structure of the whole graph. Each factor, it only needs to know who is neighbor to, and each variable only needs to know who is neighboring to. You don't need to care about the whole structure. Okay? And this is why we can apply the algorithm even if you have loops in it, because locally you don't see any loops. Okay? We just know that if it has loops, it might not work. Okay? And that's the thing. Okay? As I said, for general graph, it's not applicable. You can use the junction tree algorithm, and I'm sure Subin will talk about it. Okay? But in many cases, it works well in practice. Okay? And for channel coding, it's one of those cases. Because we're going to build a graph, so you have few loops. So actually, that's the whole point. Okay? So, and that is the thing that we will see in a minute. Okay. So we're going to stop here for 10 minutes.